Hello and welcome back to another LeetCode problem. We're looking at another interesting one. It's a medium one, 133 clone graph. As usual, we are focusing on interview preparation, so the goal is more to be vocal, to be transparent about our thought process, and to explain exactly what we're doing, which is something that people don't often practice, and often the reason why they might fail an interview, even if they come up with a good solution to the problem. So communication is key. You're being evaluated on how you approach the problem and how you think, what trade-offs you make, how you do the runtime analysis, all of those things. Besides, can you come up with a good solution and iterate on that solution to make it better? All right, so step one is read the problem description. Step two, check the constraints, then the examples, and then see if we can come up with something. Yes, so we're given a reference of a node in a connected undirected graph. Interesting. Return a deep copy, a clone of the graph. Each node in the graph contains a value, that is an integer value, and a list of nodes of its neighbors. Okay, so that's kind of the data structure that we have, right? And in Python that way. And for simplicity, each node's value is the same as the node's index. So, it's one index. For example, the first node has value 1, the second node has value 2, and so on. The graph is represented in test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes a set of neighbors of a node in the graph. Okay. By the way, this is a basic data structure that you really have to know. So if you don't know what an adjacency list is, look it up. You have to know it by heart. You have to know how to write one when you see a node, a graph, and etc. And you need to know how to read one. The given node will always be the first node with value 1. You must return the copy of the given node as a reference to the. You must return the copy of the given node as a reference to the clone graph. Okay, so we're getting a node with value 1, and the node that we return from the graph that we created must also be the one with the value 1. Okay. So here I'm just going to look at the constraints real quick. So there's a limit on the number of nodes in the graph. For complexity in runtime analysis, we're going to ignore the fact that it's bounded, but it's interesting. So there could be 0 nodes in the graph. So it could be none. We could receive a none here, right? So we'll probably, we have to deal with this in a second. Then the value of the nodes are between 1 and 100. We already know that because it's 0 indexed. And all node values are unique. There are no repeated edges. Okay, this is really important. And no self loops in the graph. So node 1 will never point to node 1. But it might point to node 2, and node 2 might point to node 3, and that one might point back to node 1. So there could be loops, but there are no self loops. The graph is connected and all nodes can be visited starting from the given node. Okay, so that's great. That's very good to know. Let's look at the example. So we have an original graph consisting of 4 nodes, 4 edges. We can't return the original graph. This is a graph that looks the same because all the edges and nodes are the same. And this one is an invalid one simply because the order of the nodes is wrong. So here node 2 is not connected to node 1, but it is in the original one. Right, so that's an invalid one. It doesn't have the same connection. Yeah, okay. So, okay, I think I've done this before, right? Yeah, I've done this before, but that's 2 years ago. So I'm going to rediscover how to do this problem. Hopefully it won't be too difficult. So what I'm thinking is, well, the first thing we have to do is we have to take care of the case where the node is none. Then we can just return none. So before I do anything else, I'm just going to add this edge case here so I don't forget. If node is none, return none. Okay, so we've dealt with the edge case that the number of nodes might be in the range of 0 to something. All right, cool. So now in terms of solution, so because we're only given a handle to the first node, we have to iterate through the entire graph, right? So that means we have at least a linear time complexity, a linear in the number of nodes in the graph that we need to clone. But we also have to look at every edge, right? So our complexity is dependent on the number of nodes and the number of edges that we have in the graph. We need to look at every single edge, and we're probably looking at every single edge twice, because if we're at this node, we're probably going to look at this edge and at that edge to see. Sorry, we're going to look at this edge from 1 to 2, and once we're at 2, we're going to look at the node from 2 to 1. And because it's a omnidirectional graph, or how do you call it, bidirectional graph? It's a connected, undirected graph. Yeah, that's what we call it. Yes, so but the time complexity will still be in linear in the number of edges and the number of vertices. And in graph problems, you know, the number of nodes typically denoted with, you know, the norm of the set of vertices, and edges is just a set of E is just a set of edges, and then we just compute how many there are. So time, and we're going to need some space complexity. And well, since we have to clone the graph, we have to use as many as are in the original graph. Now the question is if we have to do anything else. I don't think so. No, I don't think so. We will have to remember which nodes we've already cloned, so we don't clone them again. And we probably have to maintain an index that allows us to quickly look up that particular node object so that we can add it to our adjacency list. Oh, I think I skipped a little part of the example. So that gives us some information about the structure of our, let's see, the adjacency list. So we get an adjacency list, but here we're just getting a node. So maybe that's just for explanation. For simplicity, blah, 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 blah. The graph represented in the test case as an adjacency list. So I guess here, okay, so this is just for us to understand the tests. So we don't really have to care about this for the solution, because here we're just dealing with node objects and neighbors and the values. So yeah, so what I would do is we could do a simple breadth first search through the entire graph and create new nodes along the way. We could also use a DFS approach if we wanted to. Kind of like the breadth first search. But it's probably good exercise to try both. But let's do a BFS first. So we're going to implement the Python first in, first out queue, the deck. From collections import the deck. And we're going to we're going to create a queue. So this is going to be our working queue. And we're going to append the first node to it. So while we have element in our queue, that means we haven't processed all of the nodes and all of the edges. Oh, it just submitted the answer for me, but I didn't actually do anything. Anyways, whatever, it doesn't matter. And so now, when we receive the first node, we're going to iterate over all of the neighbors of that node. So for, well, in range q, length q, the length of the queue is evaluated once. So even if we modify the queue after, inside the for loop, it doesn't change how often the for loop runs. It's very nice, because we can now process all of the elements in the queue and add elements to the queue, but the for loop will stop so that the first element that we added to the queue inside the for loop will not be processed, which is nice. A nice thing to know when you're coding this type of stuff in Python. So we're going to pop a node out. That's an over-on operation in the deck, which is nice. So we fetch the element out. And now we can say the value is node.val, right? So now what we can do is first thing we can do is check if that thing already exists, right? So we have to keep track of the nodes that we've created, right? And we're just going to create a lookup table, and that's going to be a dictionary. If val not in lookup, that means we have to create it. So lookup val equals a new node with the value well, and we have no neighbors so far. No neighbors yet. Now the neighbors are actually, oh, okay, so the neighbors are probably also node objects. Yes, they have to be, right? They're not just the values, the actual objects. But maybe we do two pass. So in the first pass, we only add the value of the neighbor, and in the second pass over our cloned graph, we actually insert the correct neighboring nodes. That could be an idea. Yeah, let's see. Right, so we now added this to our values, and so this is now the source node, right? This is the source node of the source tree. Source node value, if value not in lookup. So in this thing is the destination node, right? This is, or the cloned node. So this will be the source node, and the other one will be the cloned node. And yes. Let me just see. Oh yeah, so I could make it a little bit simpler, and what I explain is that the first thing we have to do is iterate through all of the nodes in the source tree, and then after the second step we're going to add cloning all of those nodes that we visit. So visited is going to be this. If source in visited, we're going to ignore it. We've already processed that node, right? Source.val in visited, then we're going to ignore it. Otherwise, what we're going to do is we're going to iterate over all of its neighbors and add them to our queue, right? So for node or neighbor in source.neighbors, and we're going to add that to our queue, append neighbor. And what we can also do is we can also do a little check here if, and it'll just make it a little bit faster, but doesn't really change the runtime complexity. If neighbor.val in visited, we're also going to ignore it. That'll make it a little bit faster. You don't have to do that. Maybe let's just keep the code clean. Source next. Just call it like this, source next, so that we have the name source in it. All right, cool. And yes. All right, and this is a placeholder for the thing that we're going to return at the end for the root of the cloned node, of the cloned graph, which will be the node with the value 1. Okay, so this now iterates over all of the nodes in the graph, and it doesn't revisit nodes in the graph that we're supposed to clone, right? So what we now need to do is we need to create a cloned node every time we run into a new source node. And we're going to add this to our lookup. So what we're doing is we're doing the little check if maybe we should call this cloned nodes. Maybe that's a little bit more expressive. If source.value in cloned nodes then there's nothing to do. But if it's not in there, then we have to add it. So source.val is a new node that we create, and it will have the same value. Source.val And well, we don't have any neighbors to add to that yet, right? So let me think about this. How could we do this in a single pass? How could we You know, we could do things where we add to the queue also the source of the connection. We could do something with that, you know, to update or to pop out the source and the incoming edge. But maybe we don't have to do that. We could maintain a list of all the edges. That is something we could do. So we could also edges, and we just make that a set. And when we're iterating over the next node, you know, we know that an edge is basically from the source value, an edge from here, to the source next value. So that would be an edge. And if we cloned, well, if we remembered all of the edges, in the end, we can just iterate over all of the edges. We can look up the two nodes that we cloned, and we can add them to each other's neighbors list. So yeah, so let's just do that. So we have an edges. We have the visited nodes. We have our queue, and we have now traversed the entire graph. We have a record of all of the edges that we need to add to our cloned graph. We have also cloned all of the nodes already, and we can access them by value. So what we have to do next, so after this, in order to finish cloning the graph, we only need to complete it by attaching all of the edges. So, and the way to do this is we just iterate over all of the edges for edge in edges. And we know that it's this format, source, destination. So we iterate through all of them. And now we get the source node from our, how did I delete this? Cloned nodes dictionary. So this will be source. And this will be the destination. EST. And now all we need to do is we need to neighbors append the destination node, right? The actual reference to the node. And we do the same thing in the other direction where we point the edge back. So here in our adjacency list, for example, we have the edge. Let's see. So node 1 points to 2 and 4. Node 2 points to 1, so it points back, and 3. Node 4 points also back to 1. Yeah, so each node has an edge to all of its neighboring nodes, so in both directions. Cool, and finally, all we need to do, we need to return the cloned node at position 1. That's the minimum one, right? Yes. And that is if we have no value. So let me just clean up the code a little bit to make it maybe visually more appealing. Set edges, clones. We have the queue. You can also write it like this. Set of the append. And yeah. So I think that's it. I'm just gonna look through this one more time to see if I spot any obvious errors. So adding a thing to our queue, a single node. By the way, this does not add a list to the queue. It adds the node to the queue. This is a common error. If you just do this, it's not gonna work. Okay, so while we have elements to process in our DFS queue, we are iterating. Now we iterate over all of the elements in the queue. We pop the node out. If we have visited that node before, that means we don't have to visit it again. So we're just going to continue. If we have not cloned this node before, we're going to clone this node now. So we're actually adding into our clone nodes for that particular value. We're going to add that. And I see that we use source val quite a bit. Maybe we should replace that with ID. Maybe that's more readable. I don't know. Let's try that out. So that is the node ID. ID. Yes. I don't know if that makes it more readable, right? But maybe it doesn't. I don't know. That's a matter of taste. That's not that important. So maybe let's just leave it like this. Okay, and then we iterate over all of the neighbors of that particular of the neighbors of that node. And we get, of course, node objects again. So we now have an edge that we need to process. And oh yeah, so there's an error that I just saw. We're not adding the edge to our edges set. And this thing, ladies and gentlemen, is something that we will see very often. Where you think everything's correct, but when you step through it line by line, you find something that is wrong. And I'm also finding something else that is wrong. What could happen is that we put the edges in, we put one, let's say we have an edge from 1 to 2, we put that in here. And that would mean that we add the edge from 1 to 2, but also from 2 to 1. Or what happens if we have already visited that node? Then we are going to add the back edge, and we're creating the same edge and the back edge twice. So that's another small problem, because I think that was one of the constraints that I know there's only one connection between a node and another node, if I'm not mistaken. There are no repeating edges, yeah. So this solution would actually add repeating edges. So we have to take care of that. So how do we do that? Well, we know that we're visiting this node for the first time. We also know that we've already added edges from this previous node to this node. So I guess when we go through our neighbors, we should check if that neighbor was already processed. And if it was, then we should ignore it here. So what we'll do is if source next.val in visited, we're going to continue. And that now prevents us. So if let's look at this example. So if we go from 1 to 2, we know that we've already added all of the edges that go from 1 to anywhere into our edges set. So we've added the edge 1 to 2 and 1 to 4. And in our processing queue is now the node 2 and the node 4. When we process node 2, right, and if we were to add all of the edges from that node again, then we would have the edge 1, 2, 2, 1 in there, and we would add it twice when we do this. So we don't want to do that. So what we do is we check if the back edge, or if that edge points to a node that we've already visited, because if we have visited that node, that also means that we've already added that edge. Is that right? Is that correct? Maybe it's not correct. Because if I think about it further, what if we reach the node 3? You know, if we've processed this node, and this node. So all of them are invisited. But if we now go to the node 3, even, can this be invisited? No, it's not yet invisited because we have not processed it yet. So 1 and 2 will be invisited. 4 will be in the queue. Then we go to 3. We don't add the back edge from 3 to 2, but we will add the forward edge from 3 to 4. Then we've done processing this, and then we will process node 4. 3 will already be in visited, 1 as well, so no more edges are added. Yeah, so I think this should be correct. And now let's check the final part. So now we are just iterating over the source and destination node ID between where we should have edges. We pull out the nodes that belong to those IDs. Maybe we should call it source ID, destination ID, right? And then we get the source node, the destination node, and we add them to each other. Neighbots is also, that's also not the right name. So there's another typo, neighbors. Okay. Yeah, well, this took so long. Let's just run and see what happens. I hope there are no more syntax errors in here. But there's one. Well, that's obviously a spelling mistake. Let's run again. Come on, are we not terminating? If source val and visited, we continue. So we're adding actually nodes in here. And we're not adding anything to visited. Okay, another grave mistake. Visited at source.val. We forgot that. But that is why we train. We train super hard. Okay, nice. And we're actually dealing with all of the edge cases where there are no edges. So this is the case where we have 0 nodes. This we have 1 node that's not connected to anything. That's example 2. Yeah, cool. So yeah, I'm brave enough to hit the submit button to see what we get. And we get a solution that works. Nice. I don't know if there are any more efficient solutions. Let's have a quick look at that as well. Look at Python. Let's look for something where they mention a runtime complexity. I don't know why they never do that. So they use breadth first search as well that we do. A hash map solution. Well, that's what we do. We have a hash map solution with BFS. O of n plus e time and space is O of n. So here they have the same runtime complexity, but they have a better space complexity. So how do they do that? Let's have a quick look. In Python, deep copy. So they called the helper, well, they do a recursive approach. Okay. Recursive approach, base case. Let's see. So they create a clone of the node. So they use the original node as the lookup key for the copy, which is also not a bad idea. And connect all the neighbor and clone nodes for a deep copy. And now, oh, this is nice. So it's actually doing, yeah, that's actually a nice solution. I like that one. So what they do is basically, they are, so when they do a DFS, they return all of the nodes. No, they return, yeah, no, okay, yeah. So it iterates over all of the neighbors and returns a deep copy. So it goes into DFS node. It first check if the node is in the DFS. So that means we already have a copy of that node. So it just returns it. Oh, I like this, this solution. But let's try to implement this ourselves real quick. And yeah, this is kind of cool. So yeah, so now we're not doing a recursive one, we're doing an iterative one. So let's just see what we have here. We're going to have a helper method that has a node, and it's going to return an optional node as well, right? And that is that. And then here we just call the return helper on the node. Cool. All right, let's just see how that works. So it has a hash table. Then it deals with the base case. And for the cloning, it creates a clone and just adds it. And then it iterates over the neighbors and directly appends the clone of the neighbor to the neighbors list of the current node. Yeah, this is really nice. And then it just returns the copy that was created of that node. So yes, but it still has to deal with the base case. Okay, let's put this away. Let's try to implement this now from our memory. So we have still the base case. If node is none, return none. There you go. And we're going to have a hash map of copies. And what we'll do is we will check. Yeah, that's actually smart because we can use the node object as a lookup key in our hash map, right? So if the node that our helper, DFS helper function, depth first search helper, if node in copies, then we just return it. Copies node. And otherwise we need to clone it, right? So clone is node, node.val, and we have no neighbors yet. But we now iterate over all of the neighbors. So what we do here is for node in what? For neighbor in node neighbors. And we're going to get the neighbor, the clone of the, well, we get the cloned neighbor. That's what we're getting when we run the DFS helper. So DFS helper, neighbor, and this will return us a clone. And because it's a clone of the neighbor, we can add it directly to our clone neighbors list. Right. And then finally, at the end, we just return the clone. But we also need to place it into our copies thing, right? The copies node equals, yeah, copies node equals clone. And we have to do that before we call the recursion. Otherwise, we're going to be screwed, right? And we can make that a little simpler. We just do this, copies node, and then we just do that. Copies node neighbors append DFS. And we can just return copies node if we wanted to, or we could keep it like that. Doesn't matter. I think that is it. And let's just run this. Cool. So that was accepted. And remember, because we're doing, well, recursive call, the space complexity is now, well, we don't store the edges anymore, so we can remove that. But we still have potentially, well, if we have a graph that is like a linked list, we're still going to use as many recursive calls as there are elements in the graph. So the space complexity is still O of the number of nodes in the graph. Yeah, so let's submit this and see what happens. But we should be okay. Yes, and there we are. So yeah, so now we've seen two solutions, an iterative approach and a recursive one. I like the recursive one quite a bit. I'm probably going to look at this tonight again and just enjoy how beautiful this code is. And I hope you do the same.